the name of one above all and with genuine regards and greetings to whomever watching, my name is Sefer Khan, undergraduate student of nanotechnology, and today's topic is properties of nanomaterials. So without further ado, let's dive into it, shall we? Well, the topics we're exploring today is size effect in nanomaterials, quantum effects in nanomaterial, and also what is a grain and grain boundary and why is it important in nanotechnology. The big cube, or the orange big cube, is something like this. It has 6 surfaces, and the combination and summation of all these surface areas together would be equal to A1. But what about A2? A2 is comprised of so many different cubes, like blocks making the bigger cube. Well, the surface area of those little blocks are so much bigger than the surface area of the bigger one, but still the volume is same, so the aspect ratio or the specific ratio will change. We assume that each side length is 1 meter. What will happen to volume? Well, it's simple. X times Y times Z, or in this case, A times A times A. Well, that's the formula of cube. It could be different for different geometrical shapes, but anyway, the volume is calculated in this manner, and at the end you'll realize that the volume is 1 meter cubic, or for another instance, 1 cubic meter. How about the surface area? Well, as you can see, there are 6 sides, so you have to sum or add together all those sides' surface area. One side is A times A. This is the surface area, would be 1, and I have 6 of them, so 6 multiplied to 1 meter. So I have 6 squares, all 1 square meter. What will happen is that the total surface area is 6 meter squares. What about another shape? What about if I cut it into half, or even cut it into quadruple places, different shapes, different sizes? What about if I cut it to infinite amount of cubes? What will happen? Well, let's dive into it. But before that, you should remember that the sign rho, the Greek letter rho, indicates the density of our subject of study. It could be a cube, it could be a sphere, it could be a sphere of bulk material, for example, iron, air, wood, whatever you're studying. Well, the point is, rho is actually the mass of that thing divided by its volume, and we call that density. So density stays the same, doesn't matter if it's bulk or if it's as small as the nanoscale, because the mass is still the same, the volume still the same. So what will change here? As we mentioned, the surface area is changing. Well, let's divide it into 2 pieces. As you can see, the total volume stays the same, but however, we have 2 new surfaces indicated by the green arrow there, and they show that those surfaces should be added to the previous surface area in total. What was the number? 6, correct. So we have 2 new surface areas. Now, if we calculate for them, we'll realize that the total surface area of these 2 cubes now are more than the previous one. Now we go furthermore. The volume is still the same. It's 1 meter cubic. But as you can see, if we do this again and again and again, the surface area will be so much more than we anticipated. How come? Well, maybe in the first place it doesn't seem really important, but if you do it, say, for 23 times, 20 times, you'll reach to the realm of nanoscales. Your cubes would be not in the term of meter or decimeter, it will be in nanometer. So the scale is now so much reduced, thus making so much more space for our surface area. As you can see in the diagram, along with this real pictures, if you reduce the size of particles step by step, you will have a diagram that increases in its surface area whenever it reaches the nanoscale. Well, that's something to look forward to, right? Because as you reduce the size of your particle, the surface area, the atoms in the surface, will be bigger number than the atoms inside this particle. So in a really big material, for example, this computer, this laptop, the number of atoms in its surface are not really much bigger than the numbers inside this laptop, so it doesn't really matter. But if you reduce the size, the number of the surface atoms will be so much that in some point you'll have a ratio bigger. So there. Nanotechnology is where that happens. So what sorts of properties are dependent on the surface of material? Well, one of them is solutability. If you have, say, a crystalline of a salt, for example, sodium chloride, if you want to dissolve it into water, you'll drop this rock into the water. What happens is it'll take hours, maybe days. But what if you grind it into so smaller pieces? What if you turn it to the very salt you're using on the table of your dinner? What if you do it onto the water? What happens is that solutability will be increased enormously. So one of the things dependent on the surface area is solutability. But what is a catalyst? A catalyst is simply a substance that increases the rate of chemical reaction without itself undergoing any permanent change in duration of that chemical reaction. That's a good thing. Maybe it gets the reaction done faster or more efficient. Well, however it is, catalysts are important in our daily universe and daily routine. Now, catalytic activities depend on the surface of the catalyzer. Now, take for example, our famous cube is a catalyst that can absorb carbon dioxide onto its surface. Now, let's compare it to its nanoscale size molecules. Well, it simply means we're going to have comparison between the absorbability or the ability to absorb carbon dioxide onto catalyst surface in the bulk material and the same material in the nano size. What will happen is, well, as you can see, nano-sized materials go much more than we anticipated because they have so much more surface area, and the carbon dioxide is absorbed to the surface area of that matter, of that catalyst. So it's obviously a better choice for catalyzing any different sort of absorption in carbon dioxide or any other chemical reactions. Now, what about chemical reactivity? Well, obviously, chemical reactivity is same as catalyzing abilities. It depends on the surface area. Take, for instance, aluminum. We use aluminum in our daily furniture, in our houses, in our homes, as doors and windows and frames, but it doesn't go very well in oxidation, it doesn't burn, it doesn't change, it stays the same already. If you turn that aluminum into aluminum powder in nanoscale sizes, things will change so much that it burns so fast and vastly that we could use it as a jet fuel or as a rocket fuel, even, as you can see in the picture. Well, this formula is simply the amount of heat needed for a specific mass of something to change its temperature. But as you can see in the diagram, by decreasing the size of something, melting it would be so much easier. Why is it? Because the C in this formula indicates the specific heat, and C depends on the quantum and scale-sized properties of the material. So, for example, if you decrease the size to nanomaterials and nanoscales, that C will definitely change, thus making it so much easier to melt something different from its bulk to its nano size. What about physical properties? Well, they indeed change. Electrical properties, chemical properties, optical properties, and also physical properties. They all change at nanoscale. But how come? Well, take for instance allotropes of carbon. Carbon could be found in many different shapes and variations, for example, diamonds, graphite, and so many other. You can see in this shape. Now, what about their physical properties? Well, some carbon nanotubes are insulators. They're not really good conductors. Some of them actually very good conductor, even 1,000 times better than copper wire. Well, that's really indeed fascinating. Well, what happens to other physical properties? Well, strength, for example, is so much increased. A graphene sheet is actually so much stronger than diamond that you cannot penetrate it with any bullet. That's weird, right? And so many other properties, stress, strain, toughness, roughness, they all increase and they all act and behave very differently from the bulk form of themselves. Now let's dive into the fascinating world of quantum effects. So many people got scared and horrified when they hear the word quantum, but it's not really so complicated. It's just really complicated mathematics in order to understand the very nature of reality. A quanta is actually meaning discrete. For example, if you want to go up the stairs, you have to go discreetly because you go in step by step, not in a forward direction. Well, nature does that too. Now, as you remember from our first session, atoms are not a sphere, a rigid sphere, but instead they're actually waves. There are some bumps in a field, in a quantum field, say. Well, how these waves of uncertainty act in those fields. Take, for example, the band gap. Well, for describing the electrical properties of material, scientists use some sort of diagrams comprised of these shapes. The red squares are valence band. Valence band is the last boundary that electron can move freely around an atom. It means an atom has a valence band that can confine and take an electron inside some orbitals around it, and it could go on and on and on. This behavior is different in semiconductors and insulators. As you can see, there's a little difference, a little gap between the blue square and the red square of a semiconductor. Well, an electron in the valence band of a semiconductor needs a little bit bump, a little spice to move and jump from that gap into the conducting band. Well, that's how a semiconductor can conduct electricity on the electrons. Where insulators are just insulators. They cannot conduct electrons along them. And there it goes. It blocks. So why did I mention those band gaps? Well, engineering those band gaps and tuning them actually helps us to make better electronic devices. For example, transistors, diodes, and so many other electronic devices. But why is it so important? Well, for example, imagine a sphere of semiconductor material with the radius of r. It has the band gap diagram as shown in the picture, and you already know it. But if you decrease the size of those bulk materials, of those bulk semiconductors, you would realize that suddenly those band gaps you were studying getting wider and wider. It's harder for electrons to penetrate and jump over the valence band into the conducting band. So this is actually weird. Now, by decreasing the size of that semiconductor, you'd realize that band gap is getting wider and wider, which is harder for electrons to jump from the valence band into the conducting band. And also, as you can see probably in the picture, the whole integrity of blue and red squares, or red stripes and blue stripes, getting discrete, meaning they're gonna have levels. Instead of stripes, we're gonna have level. Now, instead of stripes, if we have levels, electron only can exist inside those levels. Along with them, move aside any way it wants, but not in those white areas. So that means we can tune the photonic and optical properties of semiconductors only by reducing their size. That's where we make quantum dots out of semiconductors. They're just islands of assembly of semiconductor atoms together, making quantum dots very exciting. Now, if you ask precisely, there's a lot of formulas to describe how materials and electrons and subatomic particles behave at those levels. The general formula, Eg, is the energy of gap. Now, energy of that gap equals the energy of gap in bulk material plus an extra term. That extra term is combined of those mathematical terms. H bar is Planck's constant, pi is pi number, m is the relative mass, and r is the radius of material. Well, as you can see in the picture besides it, if you reduce the size of material you're studying, for example in this picture, we're studying cadmium selenide quantum dots, and as you can see, if you reduce the size of those materials from 8 nanometers to 3 nanometers, the wavelength that they're reflecting from themselves gonna go from 660 nanometers to 460 nanometers, meaning from red to blue, and we're gonna have a shift in the color. Now, it's not only happening for semiconductors. As you know, if you reduce the size, the optical properties of a material may change. Well, in this case, gold atoms in bulk are seemingly gold, right? They're the shiny gold we all know. But if you reduce the size, something strange happens. The gold suddenly turns blue, turns red, and etc., depending on the gold's size. And that's only because of the quantum effects of quantum confinement. Quantum confinement means if you confine and limit the wave-like property and behavior of electron inside a box, and if you limit that propagation, strange things may happen. And one of them is this electro-optical behavior. Now, on the topic of grains, well, if you zoom and magnify a bulk metal, you'll realize in scales of micrometer, there are some domains, there are some structures. We call them grains. But why? What are those structures? What are those domains all side by side like Legos? Well, they're just atoms in different orientation. If you zoom onto that micrometer structure into the world of nanostructures, you realize that atoms has same direction and same orientation in each domain. But from a domain to another one, the orientation of atoms changing. For example, in one domain they may face this direction, and in another they may face another direction. Now, as I've mentioned the orientation and direction of atoms, if you pay attention, you'll realize that this disjunction and dissociation is separated by a boundary. Those boundaries are called grain boundaries. And in general, this structure is very important for us, especially in metallurgy. Why is it? Because those grains, those orientations, those directions, and those grain boundaries and separations all together will tell us the matter, the properties of that matter we're studying. But why this grain boundaries and grains, all those orientations, and how atoms topologically come together are important? Well, simply because structure will affect the property of material that we're studying. Electromagnetic waves, electronic properties, magnetic properties, strength, toughness, roughness, conductivity, thermodynamic properties, all will change because of those structures. Now, I know you've looking at those drill bits since the beginning of the video. Well, we'll get onto it right now. As I've mentioned grain boundaries and grains, well, maybe you think, how does it affect the properties of a strengthening material? Well, good question. Boundaries and grain boundaries deduce and dictate how materials should bend and act and behave in different stresses and strains. Well, if you design those grains in order to be smaller, they will be so much stronger and tougher. So, take for instance titanium nitride drill bits. They can endure 24 gigapascals, but if you make them in nanostructures, if you make them, say, titanium aluminum nitride alloy, they will take so much more energy. Like pressure would be 35 gigapascals and they can endure it. So this drill bit is actually modified with a nanostructure of titanium aluminum nitride alloy, making it so much tougher than a normal drill. And that's what we want from nanotechnology, right? Thank you so much for watching and for your time and patience. And as always, if you have any question, you could find my email and I would be glad to help you. Thank you so much and goodbye.